This video is about photoelectric spectroscopy, or PES. Now, before we begin to talk about how photoelectric spectroscopy works or why we would want to do it, let me just show you a schematic of the instrument itself. Here it is. Here is the source of radiation, in this particular case X-ray source. The sample comes in through here. You'll notice the vacuum pumps down here. That means they've evacuated all the air out of the instrument, so there's nothing in the path of the electrons. So the sample comes in here, the X-ray source comes out here. They meet right there in this middle part. Electrons are ejected from the sample. They follow this curved path here until they hit the detector. Now, the whole point of doing photoelectron spectroscopy is to see essentially experimental proof of electron configuration. So let's look at www.chemt/photoelectron.html. You may want to go to this site yourself and play around. So here's the site. Now, if I click on this hydrogen here, you will notice x-axis is energy. In this particular version, the energy starts low on the left, gets higher on the right. Okay, so energy is increasing from left to right along the x-axis. The y-axis is the relative number of electrons. So the taller the peak, the more electrons cause the peak. So this is hydrogen. Hydrogen, if you'll remember, has only one electron. And there's the peak for that one electron. It's not very high because only one electron caused it. And the energy here is 1.31. Now, remember the equation that they gave us in that handout I gave you in class? E photon, the energy of the photon, equals kinetic energy plus binding energy, or ionization energy. Remember, binding energy and ionization energy we're going to use synonymously. So in my experiment, the energy of the photons emitted by this source is known. The energy of the electrons that leave the sample is known. So I know E photon. I measure the kinetic energy. That's what the detector's measuring, the kinetic energy of those electrons. Through a simple bit of math, I can calculate this binding energy. So that binding energy is this energy in my spectrum. So there's a peak. The peak is at a certain energy, and that energy is associated with the energy it takes to pull an electron away from an atom. Essentially, it's a measure of how tightly the electron is being held by the atom. Okay, so let's think about that a little bit more. If you remember our picture of an atom, there's my nucleus. If we're talking about hydrogen, there's one electron, and it's rotating around the nucleus like that. Right now I'm ignoring this idea of electron clouds and stuff like that. But the idea here is electron, you recall, is negative. The nucleus is positive. There is an attraction there, right? Opposites attract. And they attract according to Coulomb's law, which is K Q1 Q2 over D2 equals energy. This guy's a constant. We don't care about it. What we care about is the Q are the charges. So if the charge on the nucleus goes up, i.e. we're adding more protons to the nucleus, one of these Q's, whichever Q it is that's representing positive, we don't care which, goes up, energy goes up. These are directly proportional. So the more energy in the nucleus, the more positive charge in the nucleus, the stronger that electron's being held, which makes sense, right? Because the opposites attract, the stronger the positive, the stronger that electron's being held. Now look at the bottom of this equation, d squared. So that's distance squared. This is inversely proportional. So the closer the electron is to the nucleus, the stronger the energy, which also makes sense. They're closer together, there's more attraction, it's harder to pull an electron away. So, what does that tell us? Not much for hydrogen, but when we compare hydrogen to others, it tells us a lot. Let's look at helium. You'll notice now the peak has gone from 1 to 2 electrons, so it's a taller peak, 2 electrons, and it's a higher energy. Well, it's a higher energy because now there's a second proton in the nucleus. So it's harder to pull the electrons away because they're being held tighter by the extra positive in the nucleus. Let's go down to lithium. Lithium has 3 electrons. What's the electron configuration for lithium? It's 1s2, 2s1. So if we look at our spectrum, there's the 2s1, there's the 1s2. And we know that because this is the taller peak, so that one's the one caused by 2 electrons, and that's the one caused by 1 electron. We can also say that makes sense because this guy is at lower energy. It's farther away from the nucleus, so it's easier to pull that one away, as opposed to these 2 that are in the 1s level. They're closer to the nucleus, so it's harder to pull them away. That's essentially it. Let's think about some questions that the AP exam could ask you. For example, let's say I'm going to pick one of these elements. I'm not going to tell you which one. Now, I say to you, which atom is this I picked? So you look at this and you say, okay, it's on 2 lines, but really it's just the x-axis. Here's the x-axis going from 0 to 10 and then 10 on to 100. So really this top part just kind of goes over and connects up down there. So don't let that confuse you. Okay, so I've got 3, 4, 5, 6, 7 electrons. Right there, that tells you the element. Which element has 7 electrons? Then I can also think about the electron configuration of this element. So I look and I say, okay, there's 2 together, 2 electrons in the same spot. Another place there are 2 electrons in the same spot. And a place there's 3 electrons in the same spot. And these 3 electrons are the easiest to pull out, so they must be the ones farthest from the nucleus. These here are the next farthest. And way over here, a heck of a lot more energy to pull out are these 2 electrons. So that says to me, these 2 are the 1s2 electrons, the inner shell electrons that are very hard to pull away because they're very close to the nucleus. These 2 are 2s electrons, and these 3 must be 2p electrons. So my electron configuration must be 1s2, 2s2, 2p3. Which element is that? It's nitrogen. So that's a question they could ask you. Or, you pick another element. Or they could say something to you like, justify why this peak is taller than this peak. Say something along the lines of, since each peak represents an energy level, this is an S energy level, which only contains 2 electrons, and this is a P energy level, which contains 6 electrons, and more electrons cause a higher peak, or something along those lines. And then they might say to you, why is there a larger space between here, these 4 electrons and these 2 electrons, than between these peak here with 2 electrons and this next highest peak of 6 electrons? Think about how you would answer that for a minute. The question is, why is there a greater distance between this peak with 6 electrons and this peak with 2 electrons than there is between this peak caused by 4 electrons and this peak caused by 2 electrons? Stop the tape for a minute. Think about how you would answer that. Maybe write something down. Here's how I would answer that. This is sulfur. So what you could say is, this one must be 3s2, this one must be 3p4, this one here must be 2p6. So these are the electrons on the 3rd energy level, and these electrons are in the 2nd energy level. So, remembering Coulomb's law, the binding energy is indirectly proportional to the square of the distance. These 2nd energy level electrons are closer to the nucleus than these 3rd energy level electrons. Therefore, it takes more energy to pull the 2nd energy level electrons away than it does the 3rd energy level electrons. Okay, let's look at this in dual mode. Here's beryllium. Beryllium has 2 peaks, one here at 0.90 and one here at 11.5. Fluorine has 3 peaks, one at 1.68, one at 3.88, and one at 67.2. So the question that could be asked is, this peak here, caused by 2 electrons at 0.90, is caused by the 2s electrons, the 2s electrons, let's be clear, and also this point here on the fluorine spectrum at 3.88 is also caused by the 2s electrons. The question is, can you explain why, even though both peaks are caused by the same 2 electrons, they have vastly different energies, 0.90 versus 3.88. Again, I'm going to ask you to stop the tape for a second, think about your answer, write down an answer, and then start it up again and listen to my answer. The answer here is effective nuclear charge. Beryllium has 4 protons in the nucleus. Fluorine has 9 protons in the nucleus. So there's a lot stronger nuclear force, a lot stronger positive energy pulling on these 2s electrons in fluorine than there is pulling on these 2s electrons in beryllium. That's the answer to that. Again, remember Coulomb's law. These Q's, one of them is the energy of the electron, the other is the energy of the protons. In beryllium, this Q is only 4. In fluorine, that Q is 9. That's what's making that energy go up. So that's photoelectric energy and the photoelectron spectroscopy in a nutshell.